Welcome back. We're going to expand our model now of the spread of a disease from just the I model to the SI model. So let me explain. So the first thing we need to do is we have to add a second assumption, okay, that we didn't have before. So we have assumption one, that those who have become infected stay infected and contagious. That's implied by saying that they're infected. And in the models that we'll be working with. That is what we said before, so no one gets better. Now, their symptoms might change. There might be a period where they feel really sick and periods where they don't feel as sick, but they'll always be infected and able to infect others. So that's assumption one. Assumption two is the new thing. The transmission rate is proportional to the product of S and I. Okay, so before we assume that we had an assumption that the susceptible population was infinitely large. We no longer have that assumption. We do now have this second assumption about the transmission rate. So let me explain using these boxes here. Okay, so if I look at the first box, this would be sort of the beginning scenario. Okay, so in the beginning of an epidemic, we might have, let's just say we have one person who's infected. So I'll use red circles to represent the infected people, all right? As we look at that, we have a very low I value. There's only one out of, I believe I have 20 dots there. There's only one I value. There's a very high S value, okay? So 19 of the 20 people in this model, obviously an oversimplified model, they're susceptible to the disease, but not yet infected. So the point of this is at this point, the red dot has more people to bump into than it ever could. So for all purposes, it's as if there's an infinitely susceptible population at this point in time. So this would result in the model that we had previously, just the I model, that the rate at which the infection would be increasing is a constant times the number who are infected. So because every infected person, maybe I'll add one more infected person, if they're milling around, you could almost pretend that this is a room full of people, 20 people in this case, and they're all blindfolded. And they're asked to slowly walk around. And if you get tagged or bumped into by the person who's blindfolded, you will become a tagger. So it's unlikely at this point that the two infected people would be bumping into each other. They're going to have plenty of susceptible people to bump into, and so many susceptible people to bump into that they're just not going to run out of people to bump into. So we would be back to the old model that DIDT is equal to AI, and we saw that this had an exponential growth factor to it. Okay? But now over time, as this game of tag continues, are susceptible. So we have these two who were susceptible, but they've bumped into a bunch of other people as they walk around. So let's add there are 3, 4, I'm going to go up to 10, 5, we'll add 1, 6, 7, 8, 9, and we'll add one more down here, 10. So now about half of the people are susceptible still, and the other half are already infected. So this is the sort of the 50-50 scenario. Okay. This is when the infection rates will be really high. Okay, because in the first scenario, let's pretend everybody's walking around really slowly. Each one of these, there are only 2 taggers. And if everybody's walking around in the room blindfolded very slowly, if you stop after 10 seconds, there's a good chance they haven't tagged anybody. Maybe after 20 seconds, one of them has tagged somebody, and you get to 30 seconds and another person has been tagged. But in this 50-50 scenario, we have 10 taggers walking around. So they're very likely, there are a lot of people who could be tagging, but there are still a lot of people who could be tagged. So this is kind of the optimum right now for having people quickly get tagged, because there are a lot of taggers and a lot of taggees. There are an equal number here, okay? So we have a medium amount of each. So this will end up being the sort of the fastest growth rate. This is where DI dt is maximized. All right, there are 10 people with blindfolds walking around, or 10 people who are infected with blindfolds. Everybody has blindfolds, so no one can avoid each other. But no one can target people either. They're just randomly walking around. You're going to get the most change, the fastest change in infected people when you get to this scenario. Okay. Now, if you continue the game, there will eventually just be a few who are not susceptible left. So I'm going to circle most people have now become infected. There are only a couple who aren't. Let me eliminate that one and that one and that one. All right. So now there are very few people who are left to be tagged. So this is where you have a high I value and you have a low S value. Now, while the probability of an individual getting tagged is really high because there are a lot of taggers, there just aren't that many of them left. So DI dt drops off. And eventually, you could see if everyone's tagged, then there's no one left to get tagged. So we could say eventually to 0. So when there's no one left to be tagged, obviously the rate at which infected people is growing will drop down to 0. So we're kind of slowly converting everybody over. But this is the part of the game in the middle where you have the most tagging going on, the fastest tagging. If you were to measure every 10 seconds how many people have been tagged, that's where you would see the number of people who have been tagged going up the fastest. All right. By the end, the most people have been tagged. By the time you get over to case 3, scenario 3 here, or picture 3, the most people have been tagged, but there aren't that many left to get tagged. So we're dropping off in our tagging rate. At the beginning, there just aren't that many taggers, so that's a fairly low tagging rate too. So this is a little bit like, optimizing a rectangle problem. If one side is considered to be I and the other side is considered to be S, you get the largest rectangle when I is equal to S. That's what's happening here. So our new model that we're going to have is that DI dt is not just dependent on I, it's dependent upon a constant, which we'll still call A for now, of times I times S. So if you want to determine how fast the infection rate is going to, how fast the number of infections is going up, you need to know what I is and S. So in our little analogy, you need to know how many taggers there are and how many people to get tagged, because we have a finite number now, right? So that's our model, but we need to have one more thing being true about this model. We need another statement. I plus S is equaling, whoops, erase that, 0. I plus S is going to equal 1. Okay, now remember, this is like probability. 1 represents 100%. So for now, we could say that I plus S is equal to P, the population size, but we're not going to derive this model for a finite or for a given population size. We're going to work with all population sizes, and so we'll assume that the sum of I and S will be 100% of the population. Now, what does that imply about S? That means that S is equal to the number of infected people. I'm sorry, I got that backwards. It is equal to 1 minus the number of infected people, or I should say the percentage of infected people. So going back a line, the percentage of infected people plus the percentage of susceptible people should equal 100%. So now we could say that the susceptible number is 100% of the population minus the percentage who are infected. You're no longer susceptible to it. You can't get tagged twice. Once you've been tagged, you're already a tagger. You've been infected. So now let's turn around. How does that affect our model? This says, coming back over here, we can substitute in. We would like not to have two variables on the right-hand side. So we can avoid having two variables on the right-hand side by keeping our constant, keeping the factor of I, but then changing S to a 1 minus I. So it's a factor of susceptible people becomes 1 minus the infected people, right? Now let's figure out what this looks like. Okay, the derivation of this is a bit complicated to solve for I. I will actually do that later, but let's consider what this means, all right? So first of all, let's start with when I is really, really small. It's much, much less than 1, okay? So this would correspond to sort of box 1 above, all right? We have very few number of people who can do the tagging, okay? So this would be box 1 over here, call this box 2, and I've already labeled the last one as box 3. So there are very few people tagging. So it seems like there's an infinite supply of people to be tagged. It's not infinite, but there are plenty of them around to be tagged. Okay, so what does this mean? When I is much, much less than 1, we can see that didt essentially becomes A times this I still, okay? But the 1 minus I is like a 1, okay? And if we look at this part of it, that's exactly what we had in our previous model, and that will lead to exponential growth. So we're expecting that initially we're going to have exponential growth when the infection starts out because there's an abundance of people who can still be infected. So it's very much like our model with an infinite number of people able to get infected. Okay. The second thing we need to consider with this is we have two factors. We have I. If I equals 0, that's not very interesting. If I equals 0, there's no epidemic. Okay, didt would be 0 because no one was infected and there's no one to spread the disease. What's more interesting is what happens when I approaches 1. Okay, now what does that mean? That means everyone is infected. Oh, qualitatively, we can understand if everyone's infected, the game is over. There's no one else to be infected. We can't have a growing rate of expansion of the infected population. So what happens is as I approaches the whole population, the infected rate has to approach 0, right? That's like box 3. If we look at box 3, well, again, there are very few people left to be tagged, so we can't expect that many of them will get tagged in any period of time because there just aren't that many to be tagged anymore. So that tells us something about our graph and what it would look like. Okay, so far, if we look at this model, if I look at the number of infections, or the percentage of infections, I should say, and this is time down here, we would expect that initially, we can't start at 0. Okay, so do not put a point at 0, 0. We have to have somebody being infected or a group of people being infected originally. We would expect exponential growth at the beginning, all right? And then over time, we expect that somewhere in the future, we don't know exactly where, we'll hit a leveling mark. Okay, what is that leveling mark? That is when I is equal to 1, which remember is 100% of the population. So we know our curve, we're going to curve up quickly, but at some point we have to level off to a horizontal asymptote. But there's more that we can know. We know that at first the graph is concave up, and somewhere if we're going to level off, to this horizontal asymptote, the graph has to become concave down. We can figure out where that is, all right? So we can look at the second derivative of all of this. So let's go ahead and start looking at the second derivative. Remember, that's related to the concavity of the graph. So right now we have that the first derivative, didt, is equal to a times I minus s. That's not in a very convenient form for taking derivatives. A more convenient form would be to say, oh, I am sorry. Rewind. This is 1 minus I. That was the susceptible part of the population, which is the population minus how many are infected. So now it would be much easier to do calculus if I take the ai times 1 and then distribute it times the negative I and get a minus ai squared. All right, and if we do this, we can now take a derivative. So the second derivative of I with respect to time using this last expression. Remember, a is a constant, so the derivative of the first term is a, and the derivative of the second term will be minus 2ai. Now, where the derivative changes from being concave up to concave down, where the second derivative changes from concave up to concave down, it will equal 0. So we can say that there is a point of inflection when a minus 2ai is equal to 0. And with a little bit of quick algebra, we can say that I must be 1/2. Okay, but sub that back in real quickly, and you'll see that that is the infection percentage. Okay, 50%. That is where we'll have a point of inflection. Okay, so this corresponds exactly to box 2. I had said that's where the infection rate should be going up the fastest. So if that is 1 right there, this would be 1/2. So what's going to happen if I put a little line out here, right at that point, that's where we're into the box 2 scenario. We're going to have almost, we'll have half the population infected. After that, the slope of this graph needs to start going down, and it's going to asymptotically approach all of the population. So where was box 3? Box 3 is out here somewhere. So there's box 1 in our little game of tag. There's box 2. That's where the infection rate is the highest at the 50-50 mark. And there's box 3 when almost everyone is infected, but not quite. And so this graph shows what happens in our little scenario. Okay. Now, you may recognize this curve or you may not. This is a special name. So it started out exponentially but leveled off. This is called a logistic growth curve. Now, a logistic growth curve is not just used for diseases. It can also be used for other things. So it's the spread of disease. Can also be used for population growth. The key for both of these things is there are limited resources. Okay, so in this case, in the spread of the disease, if we go back to the 3 boxes, there are a limited number of people to be tagged. Okay, so after a while, if this were a zombie apocalypse, there's no more food for the zombies after a while because everyone has been tagged, so you can't get more zombies. And the limiting factor with population growth, once again, it's often food. All right. So if this were a pen full of rabbits instead of uh, infections, and you just started with, say, 2 of the rabbits, at first there'd be plenty of grass in the yard, or clover or whatever it is that rabbits need to eat. So they would be able to eat and breed and make more rabbits. But after a while, the amount of food available for those rabbits who are born later goes down. The food per rabbit goes down, and which lowers their fertility, which means the population won't be able to continue to grow. It will grow up to a point for the resources that are present. If you then expand the number of resources, the rabbit population could grow again. Or if you shrunk them down to a smaller area, the population would actually have to drop down to match what could happen for the resource line available. So logistic growth happens. We can use it in a lot of models, not just in the model for disease. I'm going to set up the rest of this in a part 2. So let me stop this recording.